Hello everyone and welcome to this channel. In today's video I would be explaining isomerism in organic chemistry. So the term isomerism describes a phenomenon whereby we have two or more molecules having the same molecular formula but different structural formula. And the compounds that have the same molecular formula but different structural formulas are called isomers. So this is not a new word to us again, because I've heard about cis and trans isomer in our secondary school already. But in organic chemistry we talk more of other types. Isomerism is not limited to cis and trans. We have other types of isomerism as well. So in organic chemistry, we can have the following types of isomerism. So isomerism basically is divided into two, and isomerism or isomers could either be constitutional isomers or constitutional isomerism. And the second one is the stereoisomerism. Okay, so these are the two types of isomerism that we have. So we are going to be looking at the constitutional isomerism for today. In another video we'll be looking at stereoisomerism. Now, for constitutional isomerism, the only difference between constitutional isomerism and stereoisomerism is that for constitutional isomerism, the bonding sequence of the atom will be completely different, while in stereoisomerism, they will have the same bonding sequence but different orientation. For instance, consider these two compounds, CH3, oxygen, CH3, and CH3, CH2, OH, and CH3, CH3. Okay, let's make this hydrogen and this hydrogen. And the second one, CH3, C, hydrogen, CH3, and hydrogen. When you consider these two compounds over here, you will see that they don't have the same bonding sequence. That is, the atoms are not connected the same way. The CH3 group over here is bonded to oxygen, and the oxygen is also bonded to another CH3. Whereas here, the CH3 is bonded to CH2, so they don't have the same bonding sequence. So this is a typical example of constitutional isomers because they are not bonded the same way. When you check here, for this first carbon participating in the double bond, you would see that it is bonded to a CH3 group and hydrogen, and the same carbon is also bonded to CH3 and hydrogen, while the second carbon also is bonded to CH3 and hydrogen, CH3 and hydrogen. But the only difference you notice in this structure is that the orientation of these bonded groups are different. The CH3 here is bonded up and the hydrogen is bonded down. Actually, they are the same for this, but here the CH3 is up while the CH3 is down here. Hydrogen is down here, but the hydrogen is up here. So they don't have the same orientation. They are not positioned the same way in space, but they are connected the same way. So that is the difference between constitutional isomer and stereoisomerism. So in another separate video, we will be looking at the stereoisomerism, their types and possible questions you can see under that. Now let's focus on constitutional isomerism. So they also have types as well. So the first one is the chain isomerism. One of the examples of constitutional isomerism is chain isomerism. So from the word chain, it means that the isomers will have the same, number one, they will have the same functional group, but the only difference is that they won't have the same chain length. Their length, the length of their chain would not be the same. For instance, if you have butane, CH2, CH2, and CH3, and we have 2-methyl, propane. These two compounds are isomer because they're having the same molecular formula C4H10. Or you count the number of carbon and hydrogen in two of them, you see that it's C4H10. But they do not have the same chain length. This is having 4 and this is having 3, the number of longest carbon chain. So that's the meaning of chain. Sometimes they call it chain and branch because in one isomer, it will be more branched than the other one. One will probably be a chain, a straight chain, and the other one will be a branched chain. But it is a misconception that one of them must always be a straight chain. For instance, if we have CH3, CH3, CH2, CH3. This is 2-methyl-butane, and you have CH3, 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 and this is 2,2-dimethyl. Sorry, you push dash A. Okay, 2,2-dimethyl propane, and this is 2-methyl-butane. The two of them are also isomers, and they are chain isomer, but the two of them are branched. But the only difference you notice is that one is more branched. This one is having 2 branches, and this is only having just 1 branch. So that's the only difference between the isomers in chain isomer. One will be more branched, and that's the only difference. So they will have different lengths of their chain. This is having 4, and this is having 3. So that is the chain isomerism or chain isomers. Number 2 is the position isomerism. Position isomerism. From the word position, positional isomerisms or positional isomers. So the only difference is the position of their functional group. Groups like alcohol, if you have butan 2-or, as we have it here, this can be an isomer to another compound, which is the one I'm writing here, COH, This is butan 2-or, while this is butan 1-or. The only difference between them is just the position of this functional group. The functional group here is at the carbon 2, while it has carbon 1 in this compound here. So that is the only difference in position isomers. You can also have it to be the substituent sometimes. So it might not be the functional group, but just the substituent. Like if you are having compounds like CH3, CH2, CH2, CH3, CH3, and CH3. Then you're also having another one like CH3, CH2, CH3. Now we have a methyl group here, another methyl group. So the only difference you notice is that this one, if you want to name it, will be 2,2-dimethyl 1, 2, 3, 4, 5 dimethyl pentane, 2,2-dimethyl pentane. Why here it will be 2,3-dimethyl pentane. So just the position of the substituent is the difference in positional isomers. Equally, we can have 2-bromobutane, something like this, and we can have 1-bromobutane as well. So the only difference in positional isomers is just the position of their functional group or the substituents. Now don't forget, all of them are example of constitutional isomer, which we say they don't have the same bonding sequence. They are not connected the same way. You can see this is not connected the same way this is connected, and for this as well the same way. If you check the positional isomers as well, they are not connected the same way. So the functional group are not connected to the same carbon. So that is just a constitutional isomer. The next one is the functional isomer. From the word functional isomer, it means that they have different functional group. Functional isomer or functional isomerism. So they have different functional group. For instance, when you have propanone, so if you are not able to name those compounds or you cannot relate how we are doing them, don't worry, you can just check out another video I've made separately for naming of alkanals and alkanol. You can check my channel for that, you will see that. So you can learn about how to name those propanone, alkanols, like that. So this is an alkanone, which is specifically propanone, but you would see that it's having the same formula as this over here, which is propanal. So this is propanone and this is propanal. So they are having different functional group. This is the functional group of ketone, while this is the functional group of aldehyde. So they are not having the same functional group. The functional group here is just this carbonyl bonded to 2 alkyl group, while it is the aldehyde functionality over here. So that's the functional isomer. And the first example I made mention of, this example over here, or I've made it, I've cleaned. So this diethyl ether or methyl methanoate and ethanol So this is ethanol and this is dimethyl ethers. So the two of them are having the same molecular formula but different structural formula, specifically different functional group. So they are called functional isomers as well. This is an ether and this is an alcohol. And the same thing, we have propanone and here we are having propanal. So they are also having different functional group as well. So they are called functional isomers. So it can also occur in alkanoic acid as well. Alkanoic acid, like, you know, we have propanoic acid, just as what we have over here, and we have this ethers, esters. So alkanoic acid can also be an isomer to ester. So the ester over here is methyl ethanoate. Why this is, sorry, I wanted to write propanoic acid. So these two are also isomers. Just make sure you count the number of each atom that are there. You would see that they are all the same. So that means that they are having the same molecular formula but different structural formulas, specifically different functional groups. So that's what we call the functional isomers. So we'll be able to talk about the positional isomer, chain isomer, and functional isomer. So the next one now is the metamers. So for metamers, they will also be having the same functional group. They will be having the same functional group, but the only difference in metamer is that they will be having different alkyl groups. They call them metamerism. And they are called metamers. The isomers are called metamer. Okay, so for instance, if you're having like CH3, CH2, CH2, and COOCH3. So you can also have CH3, CH2, COO, CH2, CH3. Don't forget, this over here is the functional group, the COO, and what it represents is just this functional group over here is C double bond O bonded to oxygen, bonded to carbon. So that's what it represents. So you can see that these two compounds, these two molecules, they have the same molecular formula. Can you see the COOH, the COO that you see over here? This is what it represents. Now when you check, this is CH3, CH2, and we have that over here as well. Now that is what bonds to COOH, but here it is not the one that bonds to COH. Another CH2 group has been included, and that is what is here over here. Then bonded to what? CH3. So you can see that they are essentially the same. So for that reason, they are also isomers. And which type of isomer are they? They are just metamers, because at the two sides of the functional group, we have different alkyl group. That's the meaning of metamass. There will be different alkyl groups at the two sides of the functional group. So this is the functional group, the COO. So this over here, that is not enclosed. So these are the functional group, but we are having different alkyl group beside them. So that's why they call them metamass. So we can also have it in ethers as well. For ethers, we have something like CH3, CH2, CH2, oxygen, and CH3. So this can be CH3, CH2, oxygen, CH2, CH3. So these are also metamass as well. So because this is methyl propyl ether, or which one comes first? It's supposed to be alphabetically, but this is diethyl ether. I mean diethyl ether. But this one is just methyl propyl ethers. So methyl propyl ethers. So the two of them are metamass. So that's just what we call metamass. So it can also occur in amine as well. If you know the nomenclature of amine, you can check my channel for that. This is a typical example of amine. So this is having the same molecular formula as CH3 and CH3 So these two are also the same, and they are metamass because beside the nitrogen, which is the functional group, we are having different alkyl group. We are having propyl and hydrogen, but here we are having CH3 and two other CH3. So that's why we call them metamass. So this is the structure of these ones that I drew over here. So this is the structure, the complete structure for that. So that's the metamass. Now the last one is the tautomerization. Tautomerization. So the tautomerization, the most common one example is the keto-enol tautomerization. So keto-enol tautomerism, and the isomers are called tautomers. So the most common example is the keto-enol tautomerism. So, and this is the interconversion of a carbonyl, which is the keto group, into unsaturated hydroxyl group due to shifts in hydrogen atom between an atom of carbon and oxygen. And we can have it as this. We have the general formula for the ketone, something like this. It can tautomerize to ketone, enol. Sorry. So and when we say enol, when you hear in means an alkene, and we hear ol, it means it's having OH. So the only thing that just happens here is that one of the hydrogen here has shifted to this carbon. So let me just depict that with this typical example. So let's say we have this hydrogen, 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 and C double bond O, C H H H. This can tautomerize to just remove one of the hydrogens here, and we have an enol. So we have something like this. So what happened is that one of the hydrogen here has been removed and it's placed beside this oxygen over here. Now one of the bond here has also been removed and placed here. That's just the only thing that happened in keto-enol tautomerization. So we can also have CH3 and then hydrogen, and C double bond O, then let's just leave it as CH3. So this can tautomerize to CH3. Now it will always be between this carbonyl carbon, the carbon with double bond oxygen, and the next carbon to it that is containing hydrogen. So that will just be between this carbon and the next carbon to it. Now remove one hydrogen from the second carbon and then place that hydrogen on top of the beside the oxygen here to form the OH. Now one of the bond here will switch to the carbon to the bond between the two carbons. Then the hydrogen you've removed here, you have already placed it there. Then the remaining hydrogen will be here. then you join the remaining fragment to that carbon that was there with the carbonyl. You join it with the carbon now with OH. So this is the enol, and this is the ketol group. And the last one I will be talking about in these structural isomers are the ring isomerism, or ring and chain isomerism. Sometimes they call it ring and chain, ring/chain isomerism. So this has to do with having ring structures like cyclopentane and methyl cyclobutane. These two are the same, in their molecular formula, but different structural formulas. So you can also have something like an alkene like but2-ene can have a ring isomer, which is butane. Basically, all alkenes with equal number to a cycloalkenes with equal number of carbon with cycloalkenes, they are isomers. So that means that when you have pentane, it's an isomer of cyclopentane, not cyclopentane. Get that right. When you have hexane, it will be an isomer to cyclohexane. So the meaning is that they will both have the same molecular formula, but obviously different structural formula, and one of them is a ring, cyclohexane. So that's why we call it ring and chain isomerism. So there are several other examples. You can even have some heterocyclic compounds like this. So so there will also be ring chain isomers. So that's all about the structural isomerism, which is also called the constitutional isomerism. In another video, we'll be looking at the configurational isomerism and the types, and some practice problem to play with. Thanks for watching, and do make sure you like this video and make sure you share with your friends and subscribe to this channel so that whenever I release the next video, you don't miss out. Thanks for watching.